finally, the last video for this week, and we shall deal with the dependence of integrals if there are some additional parameters, which is exactly what the real life always or very often brings. So you simply have a function f, which depends on a variable x, and then some other quantities, y1 to yn, right? So for example, if you remember, we were computing the length of a curve in R3, and the length itself will be some shape which depends on 27,000 different parameters, right? And so what to do with the integration and the properties. So let's deal with the parameters one by one. So just for sake of simplicity, and nearly always it works like that, we can simply imagine that we have got a function which depends just on two variables, and one of them will be x, the one we want to integrate, with respect to which we want to integrate, and the other one, and it's just in an interval AB, and the other one will be just going in an interval CD. So in the plane, we simply would have a rectangle on which the function is defined, right? And here is the x, here is the y. And over that, we would have a function. So in each point there is some value of our function f. F depends on both x and y, and could be, say, complex or real or something like that. Right, and we say that f is continuous. Well, actually we saw this already, because f was continuous if the limit exists and is given by the functional value, and the limit is well defined for something which lives on a domain in C, and the plane is actually a C. So but here you have it explicitly in the epsilons and delta. So if I prescribe how far I allow to have the images, I have to know that there must be some neighborhood so that it's ensured if W is in this neighborhood of Z. And we say that it's uniformly continuous if this works, so the delta would be the same for all the W's, right? So for all the couples. So again, it's just absolutely the same thing as we had. And we immediately, just based on the same argumentation as we saw already, a function which is continuous on such a compact thing like a product of two closed intervals and bounded intervals will be automatically finitely continuous. And this is already proved in our observations about the topology of plane. So that's easy. So each continuous function on our interval is actually uniformly continuous. So that's great to know. And now we can easily, using the uniform continuity, we quite straightforwardly get to the result which you could think about. It's just if it's uniformly continuous in both the variables, then of course if you write the Riemann sum dependent on y, so in all of them you can make the same estimates, which is uniform, and therefore you can show easily that if the function f is continuous in both of x and y, our definition is even stronger, then the resulting integral, well, not only it will be integrable for each y separately, that's something we know already, but also the result will be again continuous on the relevant interval CD. And that's a very crucial theorem. And as you see, so the estimate is absolutely trivial, right? It just uses the uniform continuity and we are there. But this allows us to do a funny thing, isn't it? Because if we have such a function as above, so fy, that's what happens if we integrate here inside. That's the fy, and it's again continuous. So it's integrable again. So who can stop us to write the integral sign here again, right? So we have this sort of double integration. So we integrate 2 times, first with respect to x, second with respect to y. And this is just what it means. If we first integrate the first one, then we integrate the second one. And just for this very simple situation of 2 variables, there is this nice theorem called Fubini theorem. In this very simple version, it was known and used much earlier, but Fubini just put it to much more general context, which we will not touch now. So we have a continuous function on our product of 2 integrals, then the multiple integration, as in this line 1, is not only well defined, but in particular it doesn't depend on the order. So again, it's a sort of swapping of the limit processes, because it doesn't matter whether we first integrate the x variable and then the y one, or the other way around. So that's a very nice thing. And again, the proof is, it's already a little bit more tricky, so there are some subtleties there, but again, it's more or less, if you claim to your grandmother that it's again obvious because of the uniform continuity, you will not be very far from the truth. But you see that I already need a few lines to go through, and it's a little bit tricky there, but just enjoy and go through. But now there is the next miraculous thing, and this is that this very straightforward and easy use of the fundamental theorem of calculus, which tells that the Newman and Riemann approach is the same for continuous functions, and each continuous function has got the antiderivative via the integration with the upper limit as the new variable. We can prove that actually, if we have this kind of integration depending on parameter, and this function f was not only continuous in y, but differentiable in y. So if there exists a continuous derivative of f with respect to the y. So you see, in this case, we simply forget about x being a variable. We think it's a constant. We are not interested in its value. And what we do is we differentiate the resulting thing with respect to y. And then the result is that if we just are interested what will be the derivative of the resulting function f, right, at a point z, then it's obtained in such a way that I can either integrate, I get the function dependent on y, then it's differentiable and I differentiate it, or I can do it the other way around. I swap the processes. I first differentiate, right? Evaluate this derivative for y equals z if I'm interested in z, and then I integrate, and that's it. And just have a look how easy it is. So it's a nice trick. So you simply denote the right hand side here as a new function g. So remember, we assume that the derivative will be continuous, so it will be integrable, right? So this g is well defined, and f is our original guy. And so we want to show is that the derivative of the original guy is the g. So we can integrate the g, because the derivative of the original guy should be g, so f should be the antiderivative of g. So we write the antiderivative of g as h. We write it, we compute using the Fubini theorem. And using the Fubini theorem, the usage of Fubini theorem just reveals what's happening here, right? So it will be just using the fundamental theorem of calculus, it will be just this. And therefore, we see that it's just fy minus f0. So the g is the derivative of f up to a constant, right? So the f. So if we differentiate now, we see that it's really true. So that's the end of what I wanted to talk about this week. So thanks a lot, and this is it, and see you again next week.